Russia invading Ukraine has major potential effects on the global semiconductor production industry. Not because the countries host big semiconductor fabs, but because Ukraine is the world's leading supplier of neon gas. Neon gas is a critical material for the production of certain chips, and this has led to renewed concerns about another chip shortage. I have been asked to review the topic. In this brief video, we're going to take a look at how fabs use and conserve neon in the semiconductor manufacturing process. But first, let me talk about the Asianometry newsletter. I write a lot of exclusive content for it. This includes profiles on Taiwan's startup economy and scripts of previous videos like this one here. The link is in the video description below. I try to put one out every week, maybe two. Alright, back to the show. Neon is a noble gas. It is found naturally in the air at very low concentrations, roughly at levels of 18.2 parts per million. At high purity, it is colorless, odorless, and inert. Neon is most well known for its characteristic glowing signs. I remember being in Hong Kong and seeing them everywhere. All of these signs are referred to as neon, but they actually use a variety of different noble gases to generate a range of colors. Legitimate neon signs have a reddish-orange hue. The gas has large industrial uses in vacuum tubes, aerospace, chemistry, and cryogenics. In space, it is a vital coolant for infrared imaging systems. They are also used in the manufacture of OLED flat panel displays. Industrially, neon and other inert gases are cryogenically taken out of the air in large multi-million-dollar facilities called air separation plants, or ASUs. These plants are actually set up to extract and deliver oxygen to chemical and metallurgical facilities. The neon gas extraction is a byproduct of the process. As ASUs pull oxygen out of the air, they are also accumulating crude mixtures of neon and helium, referred to as NHM. This NHM interferes with the facility's main job and must be removed, but the NHM can also be purified and separated into pure neon and helium with some extra work. The process was pioneered by the French chemist and inventor Georges Claude, the Edison of France. He produced these various rarefied gas byproducts while liquefying air and first commercialized neon lighting while searching for use cases for them. His work would eventually lead to the foundation of Air Liquide, today a $60 billion company. Only the largest of ASUs find it economically viable to do the extra work to purify these gases. It costs a lot of energy to raise the purity level from 30-40% to the 99.999 whatever percent to make them suitable for industrial use. So mostly these gas byproducts are just vented out into the wilderness. The world's leading use of neon is not for lighting, but rather photolithography in the semiconductor manufacturing process. It takes up 70% of global neon production and is the fastest growing market for the $20 billion industry. Neon is a critical material for excimer lasers used in steppers for DUV lithography, like the 193nm argon fluoride excimer laser. Along with its older sibling krypton fluoride, argon fluoride lasers are the most advanced commercial photolithography systems short of EUV. Immersion lithography techniques, referred to as 193i, are technically feasible for use until the 7nm node. The economics of 7 nanometers without EUV, however, are not as clear. I did a video about this one for Patreons. Neon excimer lasers are also used for certain medical applications. The laser performing LASIK is a 193nm laser. I have also heard they have applications in nuclear fusion as well, which amuses me for some reason. Excimer lasers like those made by Cymer and Gigaphoton are used for photolithography because of their high power output, stability, and reliability. Here's how it works. An excimer laser has a cavity filled with a gas blend. What that blend is depends on the laser, but for ARF lasers, it is a mix of argon, fluorine, and neon. Despite the name, neon takes up over 95% of the mix. Along the inside of the cavity, an electrode introduces a high-energy electrical pulse discharge to ionize argon and fluorine atoms. The ions get temporarily excited and merge together into argon fluoride. This argon fluoride then dissociates back to argon and fluorine atoms, but in doing so they release a burst of deep ultraviolet photons. This is the stuff we need. The DUV photons bounce back and forth within the chamber between two mirrors. One of the mirrors is fully reflective and the other is partially reflective. When the light gets strong enough, it bursts through the partially reflective mirror and onto the wafer. The neon gas's role is to increase the excitation rate of the argon fluoride reaction. It can be replaced with helium and other noble gases, but this either does not work as well or has more substantial cost issues. Because the neon is exposed to a great deal of energetic ions inside the laser, it degrades and accumulates impurities, and thus has to be replaced every couple of weeks, either through a total replacement or an occasional partial injection. Over 50% of the world's neon is produced in Ukraine, which houses several large air separation units. In 2015 and 2016, unrest in the area led to concerns within the semiconductor industry about their availability. The industry has responded to this concern with a multi-step process. In the short term, laser makers like Cymer, reverted to older, less gas-intensive methodologies to provide 50% gas savings right off the bat. They also stretched the intervals between refreshes and injections. Engineers at Cymer have been able to reduce usage by another 30 to 50% by modifying the algorithms controlling gas injects without compromising on performance. As a longer-term solution, Cymer, Gigaphoton, and others introduced neon recycling technologies. Previously, the exhausted noble gases were vented into the atmosphere with the exception of fluorine, which is toxic and needs to be scrubbed. Now, the used gases are extracted from the laser chamber and transported to an external facility for purification. They are continuously funneled into a recovery tank underneath the cleanroom floor. When the tank is full, the air is filtered using several absorption columns to remove nitrogen, oxygen, and argon impurities. Then it is sent back into the laser chamber. The process works with about 85 to 92% efficiency, can be done within the fab itself, and does not affect laser performance. Laser energy stability remains constant and there's no new wafer loss error. Recycling neon is some 15 times cheaper energy-wise than generating more gas in an ASU. However, because the gas is a commodity and rather cheap to acquire, fabs aren't incentivized to do it for cost reasons. This is because recycling requires a re-engineering of the excimer laser design, and since the external scrubber unit also needs to be put underneath the cleanroom floor, it obviously means production has to stop. So, there's a substantial financial trade-off. Depending on gas usage rates, this recycling system saves about $450,000 a year per system, assuming a price of $3 per liter for neon. At the end of January 2022, the cost is about $9 per liter. Depending on your math, it might make more sense to just keep buying more gas, even at higher prices. Cymer back in 2016, a time of neon shortage, noted that neon recycling unit adoption across their 2,500 plus unit base was about 16%. But what if the gas can literally not be had? Therein lies the problem. In general, semiconductor companies should be thinking more about sustainability. But as is so often the case in industry, it is only when the bottom line starts getting hit that these companies start adopting the 3 Rs. For certain companies that have invested in the equipment and processes, they should be fine. TSMC, for their part, has said that the impact to their supply chain will be limited. But many other wafer fabs, especially those running DUV machines, are working on short margins, and they probably didn't do this. Unless supply can be made up by facilities in China, a growing supplier, or elsewhere, then an extended neon shortage can indeed cause supply issues. It's not their first rodeo, however, so I do suspect these will be ultimately minor. Alright everyone, thanks for watching. That's it for tonight. Subscribe to the channel, sign up for the newsletter, and I'll see you guys next time.